Hi class. I'm doing a lecture. This mostly covers 8.1, and I feel that the lectures that I provided you are very good lectures. However, I feel that some of them are missing some key information, and so that's why I'm putting a lecture together that covers 8.1 that will help you get through to the other chapters, the other sections. So light is a form of energy that can be described as a moving wave. We really don't think about light much except for when we don't have it and a blackout and so forth. But when you see a rainbow, I'm always overwhelmed at how pretty it is. And you see the colors that you don't normally see because we are not trying to refract and, separate the light. Visible light is the light that can be perceived by the human eye. Light can be refracted. That just means it changes direction through like a prism. You can see that we separate it out. Right, for now, we are going to talk about light as in waves. So you see rolling hills, and rolling hills, here's a perfect example of um, how we perceive light for this section right now. Wavelength is lambda, and it is, I'm missing a D there, lambda. Distance, it's got this upside down V in a sense, or a little bit of a Y. It is meters, but when we discuss in visual, we discuss nanometers, and you'll see why. It's a lot easier to do. We determine wavelength from, if you see this rolling hill, it's either from the distance of one point of the trowel to the other point that's next to it, or it would be the same as a crest. So we would take the point of the crest and the same point of that crest on the next hill or wave. Amplitude has nothing to do with frequency, which we haven't discussed yet. It is it's independent of all of this. This is the intensity of the wave, and the amplitude is the height. So frequency, I'm going to skip this slide and go back to it real quick. Frequency is the other thing we need to know, and frequency has to do with how many waves pass a fixed point in 1 second. So that means, this is a very bad, poor example, but it'll give you an idea. If you go to Disneyland and you count how many people go through a gate through a certain amount of time, and then you go to another gate and you determine how many people go through that in the same amount of time, you could tell the frequency of which one has more people compared to the other one. And this is the same thing. You pick a point and you count how many waves pass that point in 1 second. That's frequency. And the units are waves per second if you want to, but I really never see this one. It's 1 over S. This also means 1 over S. Or the term hertz. Hertz means 1 over second. This has to do with frequency. We're going to go more into this, but this is where this fits in. Frequency and wavelength are inversely proportional to each other. This means if one goes up, the other goes down. So if you take a look here and you see shorter wavelengths, that means that this is higher frequency. We're going to cover this later, but frequency is also proportional to energy. So if frequency is a high value, then that means the value of energy is also high. If you multiply frequency by 2, you're also multiplying the energy by 2. And the same goes if you divide. Now, since it's inversely proportional, if you have something that's higher frequency, it is a longer wavelength. So if you're dealing with a longer wavelength, you're dealing with lower energy. And you can kind of see here how fast this goes. This would be considered something that's higher energy. So you would see it more coiled over here. And as you progress to a longer wavelength, it becomes longer. So it's going to take longer time to pass a fixed point. Gamma rays, X-rays, all UV, this tends to be higher energy than the visible. And then we have infrared, microwave, and radio tends to be on the lower side. So now we're going to go back to this, and I found a nice little GIF. This could probably start hurting your eyes after a while if you stare at it. But it's good to understand higher frequency, smaller waves, and less frequency or lower frequency, this should say, bigger waves. And so that's how you kind of have to remember, if it's got a higher frequency, smaller waves pass through more. And if it's lower frequency, you have bigger waves, it's taking longer to pass a certain point. So we already covered wavelength, which tends to be when we do calculations in meters, and then we convert to nanometers when we're discussing visible. And then we have frequency, and if you multiply these together, they are equal to the speed of light. So This is a constant number here, so that means if one goes up, the other has to go down to always meet the speed of light at this value. We're going to do a problem to help understand that in a little bit. So electromagnetic spectrum or radiation, and I pretty much discussed this here, but different forms of light differ in their wavelengths and frequencies, and based on what these are, will fall somewhere in this spectrum. So you can see that the gamma rays are high energy. This is low energy. Why do we discuss the visible in nanometers? Because do you really want to deal with all these 10s to the negative 10, 10 to the 17, and so forth? No. When we discuss color, it's easier to deal with it in nanometers, because if you understand the range of the visible spectrum, you'll instantly know where that value fits and what color it is. These are just examples of some of where these fall into. Okay, so here's a visual of these waves. As you can see, radio, this means increasing wavelength. So you see these get bigger, and as you go more this way, they tend to get smaller. This is higher energy. This is lower energy if you look at visible being the middle. And so if it's increasing energy, the waves are getting smaller. And if you are decreasing the energy, the waves are getting bigger. Wavelengths of visible light. So this is what we can see with the eye. And these all have that numerical values to them. It's interesting because you see this starts at 380, this starts at 400. These are these fun little things that chemistry does that I've discussed in the past, where for some reason nothing ever just has a straight value. I don't know why people don't want to just leave the numbers with what they are. But this is still a good enough to see what these values go with and what color. So they're off a little bit, but I'm going to always say 400, 700, and if anything we do in this class is going to be between 400 and 700. It's not going to be on the outskirts of this. So one thing that you need to understand about this, if you haven't already seen it, higher energy, higher frequency is 400. It's a smaller value. Lower energy, lower frequency is a higher value. That goes against what we always tend to know about things. You need to understand that, because you might see this as a trick question, and it absolutely is not if you understand these values to an extent. I mean, you don't need to know these, completely, but you should know, higher energy goes with a smaller value than a lower energy, which is red. If you have a problem understanding this, if way back in the day when we were in Chem 10, there was, you guys used to use Bunsen burners. Orange flame, or the flame we know from bonfire, is never accepted in the lab. Do you see where it fits in here? That's because it's lower energy than the blue flame that we cook with or we want in a lab. So blue is actually higher energy than something that's closer to red or orange. That's a kind of a good way to remember this, even if you don't remember the value numbers. But you should have an idea, even with the value numbers, where these things fit in. And here is a nice spectrum. So you can see where a prism, and you can see where these break through. If you guys know Pink Floyd, it's a band. And then this will look very familiar to you. But if you don't, then you're not going to know what I'm talking about. These wavelengths, as you see, actually match to where they fit. So you can see this one's long and kind of stretched out, and these are very tight. So I like this because it actually shows you the size or the wave of what they are. And this is why we use nanometers, because having it said is 500 nanometers is easier to find it on here than to say 5.00 times 10 to the negative 7. It's a pain. So it's just an easier way to deal with stuff. I'm bringing you back to the slide because now that you are somewhat familiar with frequency and wavelength, we're going to do a problem. Calculate the wavelength of light that corresponds to a frequency of 7.30 times 10 to the 14 per second. Report your answer in nanometers. So we need to do a couple things with this. First, find out what the problem is asking. In this case, it's asking for wavelength. So this is not too bad. You have frequency, and we have it here. We know what the speed of light is. All we have to do is isolate and plug in our numbers, and we can determine the wavelength. This is where I strongly suggest that you guys get a piece of paper and write all the equations out and what they mean and the units that go with them. Because the more that you have of information, the less mistakes you'll make and the less confused you'll be with difficult questions. If you know the units that go with what these represent, then you can also catch yourself if you are going on the wrong trail and you end up with units that you shouldn't be. Or you have a problem that you just can't figure out. But if you look at the units will usually tell you what that is. So here we go. Calculate. So I pulled out the frequency. I'm giving you the speed of light. Plug it in. And this gives me my meters. So this is why we don't deal with meters when we discuss visual, because this is not going to give you an idea where it fits in the visible spectrum. So we're going to plug it in and we're going to convert it. Now, if I talk about 411 nanometers, if you go to a scale, you can figure out where and what color you can tell me that fits in. I'm not going to tell you what it is. You guys can go back and look. So now we're at a certain part where I discussed wave as light. The problem with this is that when experiments were being done, some of the results could not be explained with understanding light as waves. So what came out of that is the wave-particle duality of light, which means that one is not better than the other, but we change some of what we know to be able to explain the results that we see. So in some cases, seeing light as a wave helps explain the experimental results that we see, and and then seeing light as a particle explains other results that we see. They work together. They don't work against each other, but they help explain a lot of what we weren't able to explain with just one. So this is where the wave-particle duality of light comes in. Light is able to function as both a particle and a wave, depending on the experiment that is conducted and the observations made. So here are the conditions of what I'm talking about. Under certain conditions, you shine light through a narrow slit. It behaves as a wave. That's with a prism, you can see there. Shine it on a metal, and if it has the specific energy that it needs, it will eject electrons from that surface. And light behaves as particles of light. So this is where we discuss it as a particle, and I'm going to go into that more later. The multiple personality, which I like that your book said that. The multiple personality of light is referred as a wave-particle duality, which I've never seen it referred to as that, but it is true. Light behaves as a wave or as a particle, depending on how and what we do with it and what we try to observe. So we needed the duality of this, and we needed it when I was talking about experimental conditions. We couldn't explain some things with just the wave. And this is where Bohr's model of the hydrogen atom comes in. Not all this information do we go by anymore because we have more information to know that. But this was a good place to start. And it was the first time that certain things that we were seeing were able to be understood. So there's three postulates. An electron moves around the nucleus in a circular orbit, like the planets around the sun. An electron and its energies are quantized, which means it can only have certain values. And the change in electron's energy as it makes a quantum jump, which is electron transitions, from one orbit to another, or if you want to say level, if orbit gets you confused, to another, is always accompanied by the emission or absorption of a photon. And I'm going to cover what spectral lines of hydrogen mean right now. So let's break these down. Why was this so important? This is important because it was the first model of atomic structure to correctly explain the radiation spectra of hydrogen, which is what you're seeing here. Bohr's model explains the emission and the absorption spectra of hydrogen and hydrogen-like low atomic numbers. Bohr's model is an important step in the development of quantum mechanics and subatomic particles and its interaction and motions. So this helped explain a lot, even though we've learned enough to know what is different from this. This was what allowed us to get to the next steps. So let me explain what this is. An electron moves around an circular orbit. This is not entirely true, but this is how we teach it to allow students to understand what is going on, and it's a good visual. So we now know that this isn't true, like I said, but for the sake of learning, this is what we pretend. And This, as you can see, is an electron. The one that's closest to the nucleus is the ground state. And then if it takes a certain energy, which is photons, which are the, let's go back. Did I pass it? Oh, I went too far. Well, that's what I get for trying to, oh, here it is, photons, the particles of light with energy with no mass. So if an electron takes on a photon of a specific energy, because this just doesn't take any random energy, it has to be like a key in a lock. The key has to fit the lock in order for things to happen, a door to open, same thing. An electron has to have, it has a certain amount of energy it will need to go to the next orbit, or energy level. And that photon has to have that energy or nothing happens. So in this case, the photon comes in and it excites the electron from the ground state, which is closer to the nucleus, and then it will jump to the next level, and that is an excited level. And then it will go back down, relieving itself of that same value of energy. So the numeric value of energy that goes into the electron to excite it, it will also have to release it as an emission to get it back down to the ground state. An electron and its energies are quantized. This is just a fancy word meaning it only can allow certain energy values. A very good example of this is steps. If you ever try to walk up steps, and hopefully everybody has, or have an idea of what steps are, you can only walk on certain parts. And if you're like me, you've fallen down steps because your foot just missed or was on the tip or something. I used to be a mail carrier. I used to do this all the time. I got to the point that I wasn't even embarrassed when I fell all the time. You just can't be. There are forbidden areas that you cannot walk on. And the forbidden areas, of course, are the vertical parts, these little vertical lines that you can only put your feet on them if you're laying down or you fall. And that's exactly what this means. These are certain energy values that are allowed, which would be the steps, the horizontal parts that we can go through, and then nothing else. And that's the same. Only electrons can have only certain energy values, and those certain energy values are only place that they can go. And if it's outside of that range, they cannot go. That's what quantized means. And the change in electrons' energy as it makes so this is pretty much what I just explained. A photon will come in as a particle of light and not a wave, but we kind of use them. So if I say wave, just know that it's still light, but we explain it in just different ways, but it's the same thing. But learning the process of it, I apologize if I do that. The energy, the photon will come in and excite it, and then it will absorb. So you need to understand what absorb means and emission. When the energy is released as an emission, if it's in the visible range, we will see that as a color. Sorry if you hear my husband who's watching the Dodger game. So let me explain this a little bit more. And I apologize, some of this may seem redundant, but it's the only way that I can explain some of this. Elements that are heated emit light of only specific colors. So you're only going, when you see a color, that is a specific wavelength. And it's more of a fingerprint for that element. That element is going to give off that color. This is where fireworks come from. They know what elements give off what color, and that's what they'll use for the, sorry, everybody's calling me right now. It's a fingerprint for that color. For instance, sodium tends to be an orangey. If you guys have ever spilled water with salt in it, it gets a little orangey on the stove. That's the color of sodium. It'll never be in a green color, which would be another wavelength. It'll never conflict with that because that color that goes with sodium is strictly for that sodium color. That's a fingerprint, that specific wavelength if you looked at the numerical value. Atoms absorb. Okay, so elements are heated, emit light of only specific colors. These colors correspond to specific wavelengths and energies. That's where I say it's a fingerprint. Atoms absorb energy and transitions to another energy level. That's an excited state. So you can see here where it's written excited state. Then lose that energy. I've learned over the years of doing flame tests, if you guys remember doing the flame test, some elements the color will last longer than others. Others will be very fleeting, and I think potassium is like a pink lavender color, if I remember right. it is very quick. Like if you blink, you miss it. But then others, some reds will stay longer. And then even reds, some are bright red and some are a dark red. And they will last longer. And green tends to be one that takes forever to go away. And even when you try to clean, the green stays. So some will take longer to get down to the ground level. And once it gets down to the ground level, that means that that photon energy is gone. That's the emission part. It's gone. Electrons only absorb or emit or absorb energy only when changing levels. So that's pretty self-explanatory. Energies increase as distance from the nucleus increases. So the energy gets higher as it goes out on energy levels. And here's a little, you can see here, see the color? So when something goes through, when an electron is absorbed, it goes, let me start again. Sorry, I get tongue-tied at times. I have too much going on being home. You have a ground state electron. It absorbs energy and in a photon, in the form of a photon, and that allows it to jump up an energy level or two, depending on how much energy it's going to accept. And all of these have, like I said, a lock and a key. Certain energy values are going to excite electrons and not others. Then what happens is that same amount of energy will have to leave in order for it to go back down to the ground state. And when that happens, that's when you see the color specific for that element. Again, some of this stuff is redundant, but I made slides and then I just decided to keep them. I figure more information can't hurt. There are several orbitals. So some books call orbitals, some call levels. Just know that that's different terms for the same thing. There are several orbitals around the nucleus, or levels you can say. Electrons occupy these orbitals. These orbitals are closest to the nucleus, are the ground state. As they go further away, they are higher in energy. Atoms can absorb or emit photons. Different atoms emit or absorb photons of different wavelengths. You can identify atoms by the wavelengths absorbed and emitted. Wavelengths between 400 and 700 nanometers are invisible, and we can see those. Electrons are attracted to the nucleus. It takes energy to move the electron away from the nucleus. If the electron absorbs the correct amount of energy, it will move to a higher level. So not everything that it comes interact. So if an electron interacts with energy, it may not do anything, because if it doesn't have the correct, in a sense, key to the lock, nothing happens. Here's just another visual. So you can see, you can ignore these lovely little names here, but you can see where things get jump up and then they transition down, and they transition down in certain colors. This is kind of just to see. I don't actually know if I don't think these colors actually match this, but it gives you an idea. This is a better, so you can see that when something jumps from a higher level of N6 to N1, this is going to give off a certain color. And then this one's going to give off another color, and these are emissions. So make sure you understand the difference between emissions and absorption. And then if you're wondering, well, why does it have these colors if hydrogen only has one electron? Well, when it's in, you're not dealing with just one atom of hydrogen. Remember, hydrogen is many atoms put together. So if one electron gets excited here, another electron can get excited to another transition level. So it's many, many, many atoms, millions and millions of, Avogadro's number of atoms. It's not one by itself. It's a bunch grouped together. Energy is emitted from the atom when the electron jumps from one orbit to another closer to the nucleus. So that's going down as an emission. The colors seen produce light from a specific wavelength. So as you can see here, this is an excitation. So this is an absorption. Energy comes in. This is frequency. This is Planck's constant. We're going to work on that right now. As a photon, and it's going to excite the atom, the electron, and then it's going to come back down. Don't worry about the energy loss. I'm not going to really discuss this. Just know that the same amount that goes up has to be released in order for this to come back down to the ground state. And when it does, it will relieve that when the energy comes off. If it's in the visible wavelength, it's going to show the color. So as you can see here, this is H and nu, which is frequency. This is an equation. This is energy equals Planck's constant times frequency. Low energy photons correspond to light with long wavelengths and low frequency, and high energy photons correspond to light with short wavelengths and high frequency. So this is the equation that we're going to start using now. This is energy, and what this E actually means is energy of one photon. They don't write this, so this is something you're going to need to know, but this is exactly what this stands for. One photon, not many, one. So you can determine the energy of one photon by multiplying Planck's constant by the frequency. This is again where you need to know, you'll always be given Planck's constant. That's a given. Speed of light you'll always be given. But there are some you should know the units so you can help break down problems if the problems get difficult. So, and energy is in joules. So once you realize certain things, then it'll help you get to the next steps if you get stuck on here. So energy and frequency are proportional. You can see if I increase frequency, I'm also increasing energy. What color is a photon that has an energy of 3.28 times 10 to the negative 19 joules? Here is the equation we're going to use. We will always be given Planck's constant. We need to know what color, and we have the energy, so we have E. Here's a hint. Frequency is in both equations, this equation and the last equation we used. And we were able to determine the color from the previous equation. So sometimes you might have to use a couple equations in order to solve a problem. So this is where you definitely need to get comfortable understanding these equations and definitely know the units that go with them, because even if you don't understand a problem, if you know the units that you're seeing with certain numerical values, you might be able to figure it out. All right, so the first thing we're going to do is we're going to solve for the frequency. We know what the energy is. We know Planck's constant. So we're going to plug this in, and that's what we do here. So we plug it in, and we are given the correct units for frequency, which is 1/s per second. So this is correct. It ends in my correct frequency, my correct units, so I believe I'm on the right track. But we're not done because we can't get to color from frequency, but we can get to color from the previous equation with the speed of light. We can solve for lambda, which is wavelength. So we need to arrange this to calculate for wavelength, which we do. And now we've determined a number. Now this is where I say we don't leave numbers when it's invisible. For when we're discussing color, we never leave them in this. Because do you really know what color this is? You really don't. So you have to convert it to nanometers. This is more workable. And once you see what that is, so we got it down to 606 nanometers instead of 6.06 times 10 to the negative 7 meters. We could look and see where this corresponds in here and what color it is. So that's why we use nanometers when we're discussing visible wavelengths, because we can instantly group it and see it easier. Light absorption and light emission. Light absorption occurs when an atom absorbs light and gains energy. Light emission occurs when an atom has excess energy and gives off energy by emitting. So it's relieving itself of that. An absorption spectra, which I kind of showed you the hydrogen one, this exact wavelengths of light given off by an atom of a particular element releases energy. That's the emission. That's the same energy that it absorbed at the same wavelength. So each element has a unique absorption spectrum. This is the fingerprints. When they're trying to determine what an element is, they would use this because this fingerprint goes with strictly that element. Sunlight contains spectral light lines due to wavelengths of light absorbed by atoms of specific elements that exist in the outer layers of the sun. So they're able to determine what elements are outside of the outer layers of the sun doing this, which is really interesting. This is an atomic spectrum, spectral lines of sunlight. So I'm going to explain this, and this is part of your lab for next week. This is not difficult. This is actually pretty interesting. Substances will emit colors if they are given energy. The patterns of colors they emit is called the emission spectra. This is an absorption spectra, and I can tell you because of the black lines. An element will give off colors when heated, or a stream of electrons is passed through. That's where neon lights come from and stuff like that, if you've ever seen neon lights. Okay, so atomic spectral lines. This is an absorption spectrum. This is an emission spectrum, and these are both hydrogen. So what this means is that gas atoms absorb the same wavelengths as they emit. So they're missing from the spectrum because they're being absorbed. That's why you don't see them and you only see the black background. But in here, they come out because now they're being emitted. That energy must come out, and that's why you see them now in an emission spectrum. So they were taken in and absorbed while everything else just passed through and had nothing to do with, they didn't interact. And here, they are now being brought through and emitted. The energy has to go somewhere. So the black lines indicate where the energy of wavelengths of specific energies are absorbed. So that's why they're missing out of this. And then here they're shown because they are being emitted. I hope that's making sense. Emission spectrum. Emission occurs at the same wavelengths of absorption. The lines that are thicker have the most intensity. Some of these you can't really tell, like that one doesn't look like it's got a strong enough intensity. This one shows that it has a strong intensity. And the rest of them, that one looks like it's small. But this is a perfect example. If the line is thicker, it has the most intensity out of everything that you're seeing. And that's most likely the color that you're seeing. Photoelectric. So now that I've given you an idea, we're going to cover this more in the lab. And you can refer back to this too if it's not making sense. But next week's lab has to do with exactly this. Photoelectric effect. So now we're going back to that duality where we're not discussing light as waves, but we're discussing it as particles. So this is what I was talking about when a certain amount of energy of light is shown on the surface of a metal. If it meets that minimum energy, then electrons are going to eject from the surface of that metal. And I couldn't find a better picture of this, so I'll explain what this means as soon as I explain the full thing that's going on here. So if you shine a beam of light onto a metal surface, two things are going to happen. Either electrons are going to eject or they're not going to eject. If they don't eject, then they did not meet the threshold frequency. So that's the specific minimum energy that needs to be met for the electrons to be ejected. Shining light of higher energy does not increase the number of electrons. So even if it meets the threshold, by upping the energy value, it does not increase the electrons that are ejected because it's already met that minimum threshold. However, if the light is brighter, then the brightness of light is proportional to the number of electrons emitted. If you decrease it, then the number of electrons also decrease with it, as long as that energy value stays the same. This phenomenon is called photoelectric effect, and the electrons emitted are photoelectrons. So let me explain this. Here is that fun equation that we just learned, and this is for one photon. I couldn't find it in any other values. You can see it's up here in the values that I like, which are nanometers. But here, this is, I think, for physics. But we're not going to worry about EV. But this is still going to give you an idea of what's happening. If you look here, it says potassium. So we're dealing with potassium metal. You need a minimum of 2.0 eVolts needed to eject an electron. Okay. As you can see here, this is 1.77 or 700 nanometers. Remember, 700 nanometers is low energy. It's larger wavelengths and lower frequency. No electrons get ejected because it doesn't meet the minimum threshold. Here's about 550 nanometers. And now that if you look at the 2.25, it's above this. Electrons are starting to be ejected. So let's say the minimum here would have to be about 650 nanometers, and there's nothing in the 650 range. So it has to meet the minimum threshold for electrons to be ejected. But increasing the values is not going to make more come off. It's going to be the intensity or the brightness or the dimness of it. So this is what the photoelectric effect comes in. And this is where the work function comes in. So you see this, the energy of a photon is times Planck's constant and frequency. Well, now you can also make it the work function. The work function is the minimum energy necessary to remove an electron. So this is that minimum threshold that you want to know. And it's really easy. You're simply replacing the E with the work function. And I don't know what the symbol is called. But that's work function. We'll just call it work function. So wavelength can also be determined from frequency, but I do all of these in 2 steps. That way I understand each step and I don't get ahead of myself. So we're going to do a problem to determine the threshold of working with this. So sodium metal has a work function equal to 3.78 times 10 to the negative 19 joules. So this is also in joules. So that's our work function. Okay, that would be E, energy of a photon. So they're the same thing. We're just trying to determine the minimum amount necessary. What minimum frequency of light is necessary to remove a surface electron from sodium? To what wavelength? So this is, again, two problems in one. First, we're going to use this equation. We're going to solve for frequency. So we set it up and we get our answer. Planck's constant doesn't change. We have our work function here, and we're given it, units are correct. So we have the frequency. Frequency ties to two equations. It ties to energy of a photon, and it ties to wavelengths. So if we need wavelengths, this is the key. This is what you look for in order to get that. So we already know that. We're going to now solve for the next one. So we are now going to get the wavelength of this. So we answered the first one, the first question, which is the frequency of light. But now we need to answer the second one. To what wavelength does this correspond? So we set it up again. This is the same equation. This is from the beginning of these slides, and we convert it to nanometers because we don't leave it in meters. It's not easy to understand in that. And this, if you know that visible spectrum is between 400 and 700, you'd also know where this fits in. So hopefully, if you're seeing, these may seem difficult at first, but if you do a lot of them, they're sort of redundant. And if you understand the units that go with these, that'll also help you break down what it is. Because if you just saw this has to do with energy. There is no other problems that have just joules. Planck's constant has joules per second. So when you know this stuff, the more information you have about what you're dealing with, the less mistakes you'll make. And that's at the end. So I put this lecture together because I felt that there was some holes, and there's problems that, yes, they're done on the lectures, but I wanted to cover them myself as well. So this is mostly 8.1, and I apologize if it was a little redundant, and it will be redundant as you cover the other lectures, but hopefully the more information you have, the more it sets in and you really understand this. Also, some of this is going to cover in the lab. So it's easier if you understand it now. It'll make next week's lab really easy, which is not really difficult as long as you know this content. Thank you.